Hello, welcome to 11.4. Today we're going to be using inference to make decisions. And right now we're going to learn about type 1 and type 2 errors. If we reject the null hypothesis, but the null hypothesis is actually true, we've committed a type 1 error. If we fail to reject the null hypothesis, when the null hypothesis is false, we've committed a type 2 error. So we want to acknowledge the type of errors and find the probability that we make these errors. Now, here's a little chart to show, a little table to show what happens. So we have a decision that we base on a sample. We can either reject or fail to reject our null hypothesis. But there's some truth out there somewhere about the population. If the null hypothesis is true and we rejected it, the null, that's an error. But if it's true and we failed to reject the null, then we know that's a correct decision. If the null hypothesis or the alternative hypothesis is actually true and we rejected the null, we made a good decision. But if it's true and we failed to reject the null, we call that a type 2 error. This is a little bit difficult to understand, but hopefully as we walk through this, you'll understand it. In 11.1, we talked about the response time for paramedics. The city manager wants to test this hypothesis. The null mean, mu is equal to 6.7 minutes, and the alternative hypothesis that mu is less than 6.7 minutes. What is the type 1 error, and what are the possible consequences? So our type 1 error is we reject the null, but the null is actually true. So we reject the null. I could just say reject null hypothesis, but h to the 0 is true. So the possible consequences of that. So if we reject the null and we think that the time has reduced, but it hasn't, then what we'd be doing is we think that the team is doing a lot better than it is. So we might not think that we need to make any more improvements when we actually do. And it's possible that people die and because of the response time. Now, what is the error of a type 2 measurement? A type 2 error is we fail to reject the null. So we fail to reject our null hypothesis. So we think that we don't have evidence that it's decreased, but mu is actually less than 6.7. This is the truth, but we still fail to reject it. That would be a type 2 error. So we don't have evidence. If we didn't have evidence that it was strong enough evidence to reject this, but it still was actually less than 6.7, we call that a type 2 error. What are the consequences of that? Well, we would think that they haven't reduced their times, and they actually have. So what the city manager would probably do would put more pressure on them to continue to reduce their times, and even though they've already reduced them. I don't see any major consequences of that, other than that they just get faster and faster. Suppose the city manager wants to test at a 0.05 level. What's the probability of a type 1 error? So if we look at our normal curve, alternative hypothesis is less than 6.7. So it would have to be this far away or further in order for it to be a type 1 error. And that will occur at 5% of the time. 5% of the time, we'll get a data piece over here, even though 6.7 is the true mean. So the data of a type 1 error is 0.05. So significance in type 1 error, the significance level alpha of any fixed level test is the probability of type 1 error. That is, alpha is the probability that the test will reject the null hypothesis when the null hypothesis is actually true. So if you see this, we had a 0.05 test. The probability of type 1 error is 0.05. Now, type 2 error is a little bit more complicated. Find the probability of a type 2 error if the true mean is really 6.4 minutes. So this is confusing the first time you see it, because you aren't used to seeing two normal curves graphed together. So 6.7 is our normal curve, is our mean for a normal curve, and this is our rejection area. Now let's try to find out the value right here. So if I want to find out my x value on the bottom, we know that this is 0.05. So if I just did an inverse norm of 0.05, and then I found my my mean of that is 6.7, and my standard deviation is 2 divided by the square root of 400. This value right here is 6.5355. That's the value right on the border. So if it's less than that, we'll reject the null. If we had a value greater than that, we would fail to reject the null. So now, if this says 6.4 is really the mean, so 6.4, say, is right about here, 6.4, and so I'm going to draw out another curve. So what's the probability that I fail to reject the null of 6.7 when 6.4 is actually the true mean? So I'm going to draw this in green. In green, I'm going to fill in the probability on my 6.4 normal curve that would give us a value in the 6.7 curve that we would fail to reject this when this is actually true. Alright, so now to find this green probability, I want to find the probability that that mean is greater than 6.5355 when the mean is 6.4. So we do our mean, 6.5355, minus this mean of 6.4, and divide it by our standard deviation of 2 over the square root of 400. So that's 6.5355 minus 6.4. So I got 0.1355, and then we have 2 over the square root of 400, which is 0.1. So I have 0.1355 divided by 0.1, so that's 1.355. So now what I'm looking for actually here is these are my z-scores. I should be saying probability that my z is greater than. So probability my z is greater than 1.355. I'll do a normal CDF from 1.355 to a very large number, and I will get 0.87. 0.0877, I'm sorry. So about 8% of the time will fail to reject the null when it's 6.7, when it's actually 6.4. So that's our type 2 error. For type 2 errors, we need to concentrate on a particular value. So the particular type 2 error you want to know the probability of is if the mu is 6.4 minutes. The probability of a type 2 error is what we call beta. It's a capital Greek B. Here's another example. The feasibility of constructing a profitable electricity producing windmill depends on the average velocity of wind. A certain type of windmill, the average wind speed would have to exceed 20 miles per hour in order for its construction to be feasible. To test whether or not a particular site is appropriate for a windmill, 50 readings of wind velocity are taken and the average is calculated. The test is designed to answer the question, is this site feasible? That is there sufficient evidence to conclude that the average wind speed exceeds 20 miles per hour? So we want to test this hypothesis. The null is that the wind speed is less than or equal to 20. The alternative is that it is greater than 20. So describe type 1 error. So type 1 error would be we reject the null when the null is actually true. So we so type 1 error, we think that we find evidence that wind speeds are greater than 20 but they are actually less than 20. Now type 2 error is when we do not find evidence that wind speeds are greater than 20 miles per hour, but they actually are. Greater than 20 miles per hour. All right. So which is worse? Let's think about this. Which of these two things is worse? Well, in a type 1 error, if we find evidence that the wind speeds are greater than 20 miles per hour, but they actually aren't, that means we find a great spot to put a wind turbine, we put it up, we spend over $1 million to put it up, and then we don't get the wind speeds that we want, and so we lose out on a ton of money. A type 2 error, we don't find evidence that wind speeds are greater than 20 miles an hour, so we probably just move on to another place and search more locations that would be beneficial for us. We might have missed out on a nice opportunity to make money, but there are many places that would give us a good reading. So missing one probably isn't going to be missing out on one place probably isn't going to be the worst thing in the world. However, spending millions of dollars and not making your money back, that's a pretty big deal. So which is worse? Type 1 error. Now what alpha level do you think is appropriate? So if type 1 error is a big deal, we know our type 1 error is the same as our alpha level. So we want to take a very, very small alpha level, 0.01, maybe even 0.001. We want it to be a very small alpha level. Now if I use that alpha of 0.01, the probability of type 1 error is of course 0.01. So 1% of the time we'll actually make this error. Find the probability of a type 2 error. Our task is to calculate beta when the mean is 25. So we're looking at 20 as the mean. So let's start with our first normal curve of 20. And if it's 20, our alternative hypothesis was that it's greater than 20. So we're just going to check out here. We want evidence that is greater than 20. So it has to be that far out. Now let's find that value. So if we are using a 99% confidence interval, or 99%, or 0.01%, that's 0.01, that means 99% of the values are below that. So what I'll do is I'll do an inverse norm of 0.99. Now if I do a mean after that, and my standard deviation, which would be 12 divided by the square root of, was there 50 measurements? Yep, 50 readings divided by the square root of 50, that will give us our value right there. So do an inverse norm, 0.99, comma 20, comma 12 over the square root of 50. And I get 23.95. Say 23.95. That's the level that we reject at. If it's less than that, we will fail to reject the null. If it's greater than that, we'll reject the null. Now, this is saying what's our beta level when mu is actually 25. So let's think if mu is 25, let's find a nice beta level, or let's find our beta level. So what would fit under the 25 normal curve that would be less than this value? So we'll have to shade in all of this. So we'd say the probability that our mean is less than 23.95. That's going to be the same probability that my z-score is less than 23.95 minus 25 over 12 over the square root of 50. So 12 over the square root of 50, some answer is 1.697. And so if I took negative 1.05 divided by that, oh, I got the wrong answer. Negative 1.05 divided by 1.697. That looks a little bit better. That's the probability my z-score is less than negative 0.6187. And so I use a normal CDF from negative infinity to that answer, and that's 26%. So 0.268. So 26% of the time, I'll fail to reject the null when 25 is actually the true mean. This is what we call our beta level. Now power is the probability that a fixed level alpha significance test will reject a null when a particular alternative value of the parameter is true. This is called the power of the test against the alternative. The power of a test against an alternative is 1 minus the probability of the type 2 error, so 1 minus beta. So in our previous problem, our power, we could say power is equal to 1 minus 0.268. So 1 minus that answer is 0.732. So that is our power. So 73% of the time, we're correct when we fail to reject it when the mean would have been 25. Now, increasing power, high power is more desirable. 80% power is the standard. 4 ways to increase power: increase your alpha level, consider an alternative that is further away from our null mean, increase our sample size, or decrease our population standard deviation. Out of all of these, there's only one of them that you can actually reasonably do, and that's increase your sample size. So if you want a higher power, increase your sample size, because you don't want to change your result, or your alpha, that means you're compromising on your confidence level, um, or choosing another value further away, or you can't even decrease the sigma. So best way to do it is to increase your sample size. All right, this is your homework for tonight.